All right, welcome to the today's session of AI for All webinar series. And today we again got Kevin Galloway from Research Computing System, who is the system administrator of UAF High Performance Computing Cluster, Chinook. And today's topic is basically our lecture 4, which is High Performance Computing or HPC, a beginner's intro to HPC with Chinook UF's HPC cluster. So without wasting more time, let me hand it over to Kevin. Kevin, please feel free to share your screen. I am stopping sharing and
Okay. All right, yeah, so let me share my screen real quick. Oh,
yeah.
okay. So we're going to start off with a brief presentation, and then I'll go over some examples on how to actually use an HPC cluster. So, get sharing actually working. Let's just do that. All right, so this is going to be a brief intro to how to actually use HPC. We'll talk a little bit about how to achieve the speed up that you need when you transfer like a program from your laptop to an HPC cluster, but it's just going to be a very brief overview of how you do that and might be expanded upon in a future lecture. So yeah, we can talk a little bit about HPC, talk about Chinook specifically, and then I'll show off some demos of actually like logging into the system, using it, and kind of viewing some of the information that's going on when you run a high performance computing job. So to start off with, what is high performance computing? You may have heard the term supercomputers, cluster. A lot of nowadays you hear like AI factory. All of these are going to be some aspect of high performance computing. But what it is at its core is a lot of machines, a lot of resources somehow network together so you can use them in conjunction with one another to actually do some sort of computation. Each individual like machine is like a server that might have its own CPU, its own memory, its own GPUs, and then some sort of incredibly fast network connection in between. So you can pass messages in between and run simulations or other sorts of calculations. Generally, there's some sort of shared file system as well. So each of the nodes can write output, have input files or something like that, and all communicate and act on the same amount of data. The same sort of HPC cluster supercomputers can be used for what's called high performance computing or high throughput computing, which I'll talk about a little bit further on. They're both different ways of achieving parallelization, which is how you speed up your programs. Back in the day, it was a lot easier to get faster and faster CPU or faster and faster RAM, faster accelerators, whatever, to like speed up your program. So it was in the old days, you would just like take your program that you had on your desktop, recompile it for a supercomputer, and it would magically get faster. Due to the laws of physics, we're kind of reached some of the limits of that. So now the way to achieve this parallelization is to be able to run your computation on a lot of machines at the same time. And we'll talk a little bit about what that entails. And finally, most HPC clusters are what's called a shared system. So you're sharing the resources, both like the computational resources, like all the GPUs, all the compute nodes, all the servers with other researchers, and also like the login nodes and stuff. So you have to keep in mind that you might not be able to access the resources immediately or exactly when you want. And whatever you're doing on some of the shared nodes, like login nodes or data transfer nodes, is going to affect a lot of other people. So it's just generally a good idea to try to be a good neighbor in these cases. And so this is a brief diagram of kind of how you access an HPC system. On the left, you're kind of on your workstation. This could be like an SSH terminal. It can be a like web interface, and some programs like Jupyter Notebook or MATLAB can also allow you to directly access HPC resources. Generally, you somehow connect through a login node, and then from there, you ask the HPC system through a job scheduler for resources, and then it gets allocated on the compute nodes. On the compute node side, each of these colors is a single job. So you might be using just a single node. You might be using like 5 nodes that are all contiguously together, or you might be using just a scattering of nodes that are nowhere near each other in the data center. Some HPC centers as well make you actually share individual nodes as well. So you might get 12 CPUs on a 24 core system and someone else has the other 12. Um, there's a lot of different ways you can kind of share these resources. Um, so it's just kind of depending on what center you're at, you're going to have to keep in mind what sort of workflows you can run. Before we get too much farther, there's probably a lot of terminology that I'm going to be using that I just kind of want to briefly define. First off is a job. This is a request to the job scheduler for resources. And the job scheduler is a program that manages the resources that a HPC cluster has access to. So the job scheduler will know what compute nodes are available, what types of compute nodes are available, and what users can access certain nodes, certain partitions, certain groups, and also has some knowledge of allocation, which I'll talk about in a little bit. There's usually a queue. This is just kind of a list of all the jobs that are submitted to an HPC cluster. So you ask for resources, the job scheduler will try to um, manage these. And if there are more requests than there are resources, some of them get put into a line, a queue, and have to wait to be launched. And a lot of job schedulers have complex scheduling algorithms based on a variety of sources that a variety of data that will um, place it into allocate it actual resources based on a whole lot of things like how long it's been waiting, the amount of resources, if projects have used more than their fair share. There's a whole lot of things that can go into these calculations. I've used the word node a lot. A node is just a single machine or server. There's many different types of nodes. Generally, there's like a login node. This is where you're actually logging into a system and accessing it, accessing like the job scheduler and things like that. Um, Generally, you don't like walk up to a screen and a keyboard and just like go up to a login node directly. You're accessing it through some network protocol, SSH, web browser, something like that. Uh, Part of this is because login nodes are shared, like I mentioned before, so you can't really have one person at the keyboard trying to do everything. The compute nodes are where jobs are actually run. This is the actual computational resources. Compute node might be just a CPU node. It could also be like a GPU node. It might have GPUs in there or other accelerators. And generally, there's also many different types of like compute nodes. Some might have a lot more memory. Some might be what's called like an interactive node where you're allowed to log in and run stuff in an interactive fashion, usually for like debugging, or if you're running a program that really does have to run interactively. Generally, there's 3 or 4 different types of directories that are going to be available on an HPC cluster. Most HPC clusters run Linux, so you're going to have your home directory. Generally, these are used for like your configuration files, and on some systems like Chinook, it's where you want to try to store your programs if they're small. They don't take too much space, and it's kind of something for like executables, configuration files, output, things like that. Output of Slurm jobs, not your data output. Generally, there's a scratch directory. This is some storage that's usually not backed up. You usually get a lot more of it. It's usually on what's called a high performance file system, which is just a file system that's tailored for parallel file access, parallel like striping of files. And so this is usually for like input that can be re-downloaded, temporary files, or your output before you transfer it somewhere else. The big thing about most Scratch directories is they're not backed up. And some centers also have what's called a purge policy, where like if files in there haven't been touched for some amount of time, they'll be automatically deleted. We don't do that here at UAF on Chinook, but a lot of other centers do it. And then they also get a little mad if you try to game the system by like accessing the file, even if you're not using it. So kind of don't do that either. Sometimes there'll be an archive directory, which is kind of a longer term storage. Um, this is usually like maybe tape backed. It will be backed up. And if it's taped back, all this really means is that there is a physical, like magnetic tape that will store the data on it. And then there's a tape silo that will put tapes in drives to get the data off of it. What this means though is it's really slow. If you have memories of using like a VCR, um, you literally have to fast forward or rewind the tape to where the data is. And then it has to be copied over to something that's faster, usually like a spinning disk cache. So basically what this means, if it's put into archive, it's something you don't need to access all the time, usually like weekly, monthly, something like that. Um, One use on Chinook, for example, is if you do have a lot of input data that's larger than your scratch directory, you can put a lot of it into archive and pull out the data that you need, transfer it to center one, which is our scratch directory, run your analysis on it, delete it, and then pull the next batch of data to it. You never want to run any calculations directly from archive because it'll be very, very slow, and our compute nodes can't even access archive. Talked about nodes, single machine or server. A core is a single CPU or CPU core. This will be pretty important because when you're asking for resources, a lot of the times you can ask for nodes, you can ask for cores, and then on top of that, you might be using a multi-node parallelization scheme or a multi-core parallelization scheme. And these mean different things. If it's multi-node, that usually means you need some sort of networking interface to be able to communicate between different nodes. Whereas if you're doing like a multi-core, you're confined to a single server, but you can make use of all the nodes on it. And finally, there's one that's pretty common to a lot of HPC centers is what's called an allocation. And a lot of centers, when you want to use their HPC resources, you have to kind of like write up a request, explain what you're doing, and then you have to kind of estimate how many resources you want to do. The HPC center will get that, and then they will allocate you a number of what's called like core hours um, to your project. And so this is basically a calculation that takes into account like the number of CPUs, the number of GPUs, amount of memory, just the amount of resources that you're using, and then gives you like that per much per core hour. And each time you run your program, it will use some amount of core hours. And when you hit zero, you won't be able to run on their HPC system anymore. And you have to like re-up your allocation. Here at UAF, we don't make use of allocations. Our kind of similar scheme is we use what's called prioritization. Um, Basically, certain users, if they've like, I'll talk a little bit more about this when we get to the Chinook specific section. But basically, certain users will have certain priorities and they'll just be bumped up in the queue potentially, be able to run their jobs first. But otherwise, you can use the system as much as you want. I'll go over some kind of standard, and I use this in quotes because each center is different, HPC practices as well. To start off with, as I mentioned before, you're going to be accessing the HPC cluster remotely. You're not going to go into a data center and like hook up a monitor, a keyboard, and a mouse to a screen. Um, this is for a variety of reasons. One, you don't want to have to actually be in a data center trying to type stuff out. Very loud, noisy, and cold in there. Um, and two, each of these clusters are going to be shared resources. So your remote access is going to be via like SSH, via like your laptop or workstation. Some centers allow you to like, not some centers, but there are actual like SSH programs on your phone, tablets, etc., that you can also use in a pinch. Some centers use what's called Open on Demand. It's like a web browser that gives you like a job composer. You can actually log into the command line interface directly, and then also they have what's called apps, such as like Jupyter Notebooks, MATLAB, etc., that you can also launch to access the HPC system. Finally, like Jupyter Hub and some other programs I mentioned, MATLAB, will also have potentially methods within them to also access HPC resources. Usually it will talk to an intermediary server and then be able to like launch a job on the actual compute nodes. Uh, Um, most HPC centers have a job scheduler, Slurm, PBS, Flux. There's a whole lot of these that will manage resource allocation requests. So Um, a lot of these are pretty similar in how they're used. Some even have like wrappers that allow you to use like keywords or um, executables, executable names from other versions to submit jobs. Um, but it's just a way to manage your resources, manage your requests. And then a lot of centers will use queues or partitions as a way to group their compute resources. So you might have a like GPU partition for all your GPU nodes. You might have like an AMD partition, or you might go kind of at a higher level, which is what we do here at on Chinook, where we have basically a small and standard partition. The small partition is for jobs that only use like one or two nodes, and then we have a standard partition, which is like 3+ nodes. But so most centers will have some sort of partition you need to submit your job to. Software is generally accessed via modules. One of the big things in a lot of academic HPC, at least, is you want to be able to reproduce the work that you do. And so when an HPC center installs software, they might need to install multiple versions of the same piece of software because you want to keep stuff updated, but someone might be using an older one. And so you don't want this to just kind of automatically be added to your path. So this is all accessed via modules, which I'll show you some examples of. And all a module really does is set a bunch of environment variables, usually like a path, an LD library path, a C path. So this will tell you where the executables are, where any shared libraries are, and other stuff of that nature. Generally, there are multiple node types. Login nodes are very common. That's where you kind of do your compilation and copy files and do stuff like that. On it, there might be some interactive nodes, either for doing interactive work on the compute nodes or maybe just like a more intense login node to do like post processing or analysis. Generally, there's compute nodes where the actual work is done. These can, as mentioned before, be just CPU, can have GPUs as well. Generally, most compute nodes, though this has changed a lot with the advent of AI and more of the GPU um, nodes, but generally, most compute nodes don't have hard drives in them as well. There's usually no um, persistent storage on there aside from shared file systems. This, as I mentioned, this is changing a bit with GPU nodes because a lot of the AI models want to store some data on there. Um, the thing to keep in mind on those though is any persistent storage that's like directly hooked up to the GPU, like an NVMe drive that's on a GPU node, generally will be wiped after your job's completed. And finally, a lot of centers have what are called data transfer nodes. These are usually like a Globus endpoint or a place where you can do rsyncs or parallel copies and stuff like that without needing to use like a full compute node. And you're also not using like a login node and interfering with everybody's work. Finally, most HPC clusters have what's called a parallel or high performance file system. Um, Basically, the way these work is there's like a metadata server that will tell like a file system where your data is or where a file is, and then it'll have actual storage targets where it will have either like the full file or chunks of the file. And this is done so like if you have like a really large data set that you're working with, like say you have like a terabyte of data in a single file that you're working on. Um, if it's split across multiple storage targets, your program can theoretically, depending on how the data is set up, access multiple parts of the file at the same time, um, which can speed things up. One caveat with basically almost all file systems, but parallel file systems in particular, if you have lots of small files, that generally bogs down um, your performance if you're accessing them. This is usually uh, because you have to hit like a metadata server first and then go out to the file to access it. If you're doing small files, you can do a lot of these operations at once, and it just bogs down the metadata service. So, talks about what HPC clusters are. We'll talk a little bit now about what parallelization is, or basically how you speed up your program. As mentioned before, we have diminishing returns on increasing CPU speed. Um, we're still obviously increasing how fast CPUs can go, but we're not making those leaps and bounds that we're making in like the 90s and 2000s. So you can't really just move your kind of single threaded, single process code to a new CPU and hope to get, 2 or 3 times the speed. Additionally, we can always add more CPUs. So if you're working on a cluster and say you have a giant, massive simulation that uses every node and you're still not hitting the performance that you need, if it's parallelized, you can just always add more CPUs and more nodes and get that increased speed up. It also allows HPC clusters to stay around a little bit longer because you can keep adding newer resources without having to like get a whole new system. There are 3 main types of parallelization that typically happen on an HPC cluster. The first is multi-core. This is kind of the easiest, quote unquote, where you're usually confined to a single node. That's only partially true because you can use multi-node interfaces to run multi-core processes on multiple nodes, but if you're just multi-core, you're confined to a single node. Traditionally, the big program to do this with has been OpenMP. It's just a way to, when you're writing your code that uses OpenMP, to um, have your code run on in a threaded format on different CPUs, and there's whole bunch of different like settings you can use when you do OpenMP, and then it will usually, after it's kind of run all the stuff it can all at the same time, it'll reduce it and combine it into whatever you need it to. The other way is background processes, and this is kind of the um, way to do it if you're using more like the high throughput computing way, which we'll talk about in a second. But basically, if you have like a program that only runs in like a single thread or runs on a single core, if you can somehow take your data and run your program on only like a subset of that data, so like if your data is kind of independent, you can just run as many background processes as you want, all at the same time, each using a single CPU, and you might get some performance increase that way. Multi-node is usually some way where you need some sort of networking interface. The traditional HPC way has been using MPI, or the message passing interface, where you basically have a control program that kind of knows what its ranks are and what nodes are communicating over, like what rank it's using. So it can kind of redirect computations to different nodes based on this and different cores. Other ways you can do this is you could literally spin up like a client server architecture. I think there's some parallelization schemes that kind of do that, where they have like a control server that can then spawn processes on these client nodes that it starts on on other compute nodes, and they can communicate that way. And finally, there's the GPU, graphics processing unit. I think they may have changed what GPU stands for with all the AI stuff. Generally, you're going to be using CUDA or OpenCL through this. CUDA if you're on the NVIDIA side, OpenCL if you're on the AMD side, and then XPU, I think, for Intel. I know that AMD also has um, what they call a translator, where it tries to translate their OpenCL to CUDA. or actually, sorry, your CUDA to OpenCL, HIPAAFI or something like that. But they're not one-to-one or changeable. You're going to have to tweak that.
So here I have a question. So, like NVIDIA has this CUDA programming interface. Does AMD GPU has a different types of programming
Yeah,
interface? Is it
I think it's OpenCL.
it is
I
OpenCL?
think so, but I might be incorrect on what they're calling it. Because from my understanding, what AMD ended up doing once AI really blew up is they kind of converted their interface to look a lot like CUDA, except I think when you run CUDA, you have like CUDA underscore whatever the function is. In AMD, I think it's HIP, like HIP underscore whatever, and that's how they get their translator to work as well, because they're trying to match the arguments that CUDA uses. But yeah, so
Does Chinook have any AMD
uh,
GPU
we
in it?
don't have AMD GPUs on Chinook. We do have AMD processors on our GPU nodes, which is, we'll talk a little bit about that once we do the demos. But um, theoretically, it shouldn't matter. But in with GPUs, we have found that you want to compile your code on the GPU nodes. Otherwise, we've run into some issues, even though theoretically they should be compatible. Yeah, and I assume Intel also has its own interface. I know if you're doing like PyTorch, you have to specify if you're using CUDA, OpenCL, or the XPU. All right. So the two main types of computing that you'll see on an HPC cluster are what's traditionally called like high performance computing or high throughput computing. Your high performance computing is usually if you have like a complex analysis that really needs a lot of different calculations, but they might not be independent of each other. So you might be able to do some of it in parallel, some of it might need to be done in like a serial fashion. And this is all going to be in like a single unified program. A lot of this, one example of this will be like a lot of weather simulations because you have so many variables, like, you have to have your wind speed, you might need to have your, maybe some tidal or ocean metrics. You might need some like precipitation stuff that's all feeding into each other. You can't do a bunch of calculations independently and then combine them. They all have to like kind of work with each other. Or if you're doing like a time series analysis where you need, um, the previous year's calculations to feed into the next one, you're not going to be able to kind of separate that into multiple independent programs. Um, So that's kind of your kind of high performance computing approach. This is usually done through like MPI or something, um, and usually takes a little bit more work than doing the high throughput computing approach. The high throughput computing is if you have like a single program that just needs to act on different sets of data, or maybe even just different inputs for the same data, but like you need to run a ton of these. So if you're like maybe analyzing genomes or something, like you're just trying to classify them, or you're maybe looking for a specific, string in a genome, you might be able to run your program, which is maybe like a single-threaded program, looking for that on your entire set of data. Or if you can break up your data into chunks, like, 1,000 genomes at a time or something, instead of like the million that you have, you can run your program searching for, that string in there, on these smaller subsets all at the same time. So your program itself might not be parallelized, but you're able to run that program on subsets of data all at the same time. And then you just basically try to flood a system with as many of these as possible as you're allowed to use, or as many as you can kind of split up. And at RCS, we see this a lot with R program. Someone will like write an R program on their like laptop. It'll work on a like, a set of data, but they can run their R program on only like a subset of it and then do that multiple times. And this is like kind of the cheap and easy way to transfer like a single process, single threaded program to um, an HPC cluster. So now that we've kind of talked about HPC generally, I'll talk specifically about Chinook now. Right now we have technically 4 different types of nodes that are available now. with a couple of extra types that are similar. But we have basically four generations of nodes now. Our oldest are 28 core um, nodes. These are our oldest. And so as we were kind of like slowly phasing them out as we get more compute nodes, but we have 28, 40, and 48 core nodes. These are just CPU nodes. And then the fourth type of nodes that we have are GPU nodes. Our 28, 40, and 48 core nodes all use Intel processors, three different generations of them, which basically means if you're compiling something and you want it to run on all of our compute nodes, fortunately, you have to compile it on the 28 core nodes just because newer nodes might have other processor features that the older nodes don't have. And when you compile, it might use those, and then it won't work on the older stuff. Our GPU nodes have AMD EPYC processors, and then we have two different types of GPUs available, L40S nodes and H100s. What we have found, even though technically AMD and Intel are supposed to be kind of like instruction compatible, we found that if you're like trying to do like Conda environments with GPU things on our L40S and H100 nodes, but you compile that or try to build it on an Intel node, it runs into processor issues. So if you're doing Conda environments, Python environments for GPU functions, we very much recommend that you do that on one of the GPU nodes or on our GPU login node, just to kind of avoid that. Chinook uses what's called a condo model, and this is why we have three generations of nodes. Basically, instead of, oh, go ahead.
One question
Yeah.
regarding that, this AMD versus Intel thing. So,
Yeah.
Yeah, I mean, when it comes to this container environment, like let's say Singularity or Docker,
Yeah.
how does that impact? Does that all impact AMD versus Intel or really?
We don't have too much experience with that. I have a vague memory that it might matter a bit, but I think theoretically containers shouldn't. If all goes well, it shouldn't matter. Yeah. The bigger thing that we found with containers, and I think I'll talk a little bit about this in a future lecture, is the container that you're trying to use can't be too much newer than your like the base OS. Usually like one or two version, like usually that's like two or three versions ahead. And this might also be more of a Red Hat specific thing, but we did run into a little bit of that. And for the technically minded out there, that's just due to most all Linux systems have glibc attached to it, which is like a core component. And if that drifts too far between like your container and your base OS, sometimes you run into issues. Yeah. So Chinook uses what's called a condo model. So a lot of centers, if they're able to, basically what they end up doing when they get an HPC system is after it's run for a certain amount of time, they decide to retire it and then they basically buy a whole new system. As servers, computing stuff has gotten more expensive, or um, as people have realized that, some of the hardware that they were getting rid of was still usable and still good, another kind of model came around, which is called the condo model, where researchers can buy individual nodes, add them to the cluster, everyone gets more resources for it, and then they get certain perks and privileges. On the Chinook side of things, basically, they can make what are called reservations if they need, so they can get like uninterrupted access to nodes for a certain amount of time. They get like a bump in priority and extra storage. But it also benefits everybody else because when they're not using those nodes, everybody gets access to them. A lot of universities have kind of gone to this model for some of their clusters just because it's kind of like win-win for everybody and also keeps hardware around for longer and, it just gives more resources to everybody. Chinook uses Slurm as our job scheduler. This one is pretty common around most HPC centers. It's also you have any experience with PBS, there's a wrapper around Slurm that allows you to use like PBS commands with it as well. And then we also use LMOD for our module system. So basically, this is just a program written in Lua that kind of handles setting up modules, loading modules, looking for modules, etc. And I'll show some examples of that when we get to the demo section. Chinook's home directory is 50 gigs. In our case, we want you to use that for like scripts, codes, and smaller user-built software if you can. This is on a not parallel file system, so small files aren't as big a deal for this. We have Center One, which is our Luster file system. This is our Scratch file system. It's parallel, as mentioned before. It's really bad on lots of small files. And again, not backed up. So we want to use this for data that can be like downloaded again in a pinch, and it's typically used for like inputs and outputs that need to be copied to another location. Forgot to put it on here. We also have a BGFS file system that we're slowly spinning up and getting people access to. It's another parallel file system, just basically a different flavor of it. And this will offer a little bit more space available to projects. And because it's on newer hardware, we expect it'll be faster, but we're still running some benchmarks on it. And finally, we have Archive, which is our magnetic tape back archive. It's about 7 petabytes, used for long-term storage that is accessed as infrequently as possible. One thing to be aware of with Archive is your data might be in a disk cache or it might actually be on tape. So the way this works is when you request some data from tape, in the tape silo, a robot arm will go put the tape into a drive and then copy it to a little disk cache so you can access it quickly for a time. This disk cache is much, much smaller than the total amount of storage that's available to the tape library. So stuff moves in and out of cache pretty quickly. So you can't guarantee that your data will be staying in that cache. And then finally, there's this batch stage command that you want to be aware of. Basically, because data is on physical tapes, when you want to pull that data back, you want to tell the tape silo, the robot, and the program that manages all that where all the files are, so it'll try to grab the tapes in as few operations as possible. So like one example of this is, say you had 1,000 files on tape. All your even files are on tape 1, all your odd files are on tape 2. If you don't use this batch stage command and you want to move all those files to this disk cache, basically what the tape library is going to do, the robot arm is going to take tape 1, grab the first even odd file off of that, file 1, copy that file to the disk cache, take the tape out, and then grab tape 2 to put file 2 into the cache, put that tape back, and then grab the first tape for tape 3, and just keep alternating like that. When you use this batch stage command, it tells the tape library and its software, hey, 500 of the files are on tape 1, grab all of those first, copy them to the disk cache, go to tape 2, grab those 500 files, move them to the disk cache. So instead of having basically 1,000 operations that you're doing it in 2. It'll be much quicker. The software that's on Chinook is kind of broken down into a few different ways we've installed it. We installed some software directly on the system. The big one for this is basically Singularity and Aptainer. We generally shy away from using like Linux's package manager to install stuff, just because it makes us a little bit less flexible for installing software on the compute nodes. For example, if we were going to install like OpenMPI, like we wanted to install multiple versions of OpenMPI using the package manager, each time we kind of wanted to update or do something like that, we'd have to run that command on all the compute nodes. And then also then in our like golden image, install it there. So it just adds multiple steps and also might interfere with work that people are doing. So we use this product, this framework called Easy Build. It's written in Python. You pass it what are called recipes to basically build software. It's built based on what are called tool chains, like what compiler are you using, what version of MPI you're using, are you using CUDA? And it's just it's kind of open source product that was built to make installing software on an HPC system easy. Um, Another one that you might hear about that's pretty similar is called SPAC. I'm thinking a future lecture we'll be talking about this because users can also use these two programs themselves to build software as well. And then also, there's user-built software either using something like Miniconda, Mamba, things like that. We do recommend nowadays that you try to use Mamba over like Miniconda. It has a faster dependency solver, and I think has these environments that you build using Conda have gotten more complex. The Conda dependency solver just takes forever, and sometimes we've seen it lock up machines before. Um, Also, some people will just, compile their program using whatever compilers are built. And RCS is always happy to help you build your environments, compile your programs. Any of our software that we build using Easy Build is going to be accessible through this LMOD module system. And these are just some commands that are pretty useful. Module list will show you what you have currently loaded. This can be useful both when you're running jobs on the HPC system or if you're compiling and running into errors just to see what you have loaded and maybe you might have like incompatibility somewhere. Module purge will remove all your modules. This can be really useful when you write like a batch script to basically start from a clean slate when you're submitting a job to the Slurm job scheduler. Slurm tries to pick up some stuff from your current environment, and we've seen that um, sometimes cause issues because you might have like a library loaded that you didn't remember that you had loaded or something, and then when the job goes to the compute nodes, it might cause a conflict somewhere. Um, Module avail will show you what modules are currently available to you. Our module scheme on Chinook is called a hierarchical scheme. Basically, what this means is as you load modules, more modules will become available for you because you have like the prerequisite. I'll show some examples for that. So then module spider is how you search for specific modules. And I'll show all of these as an example. They're all pretty useful commands and are really the reason why we switched from the old environment system to LMOD. And just since this is, Chinook specific, anyone at the University of Alaska can get access to Chinook. Basically, though, it does require that you have a principal investigator. This is typically like tenured or tenure track faculty, research faculty, or emeritus faculty can usually serve as PI. Other groups can as well. If you're not in kind of that group, but you say you want access, still contact RCS. We'll work something out with you and figure out who needs to be your principal investigator. And you can go to this URL, basically our homepage, to get more information on that. Yeah, and it doesn't matter if you UAF, UAA, UAS, anyone can get any UA member can get access. So now we'll talk a little bit more about actually launching jobs, what Slurm is, little things like that. As mentioned before, Slurm is our job scheduler. You put together a request for resources using the srun or sbatch command. This request gets bundled to the job scheduler. It will look and see what resources it has available and then allocate them to you and run what you asked it to run. There's lots of utilities to display specific job information. These can be useful for seeing jobs that are currently in progress or have already run. You might want to be looking for like historic data as well. So the SQ command is kind of your basic, what's the state of the current queue, for example. It'll show you what jobs are currently running, what ones are waiting to run. RCS has also developed a program called QMap that we have on our login nodes that will also show the same information as SQ, but in a little bit more of a organized graphical way. SQ also has a bunch of flags that you can pass it if you're only interested in like running jobs and stuff like that. There's the SACCT, S account command. This will view like the current state of the job. So you do like S account dash J and then like a job ID, and it will give you some current information like when it started, how long it's been running, what nodes it's on. It has this dash O flag. I might talk about that in a little bit, that you can pass all sorts of outputs, like if you're more interested in specific information. And then you can also use this S account to view historic job information as well. This can be useful if you want to look at some past jobs, like if, for example, you think your program is getting slower for some reason, like you've been running the same types of simulations for a while, you can kind of get the elapsed time for all your like previous jobs and your current ones and be able to compare. We have about 7 partitions on Chinook, partitions or queues. I think I have a little bit of a table about with a little bit more information about them in a second, but you can get most of the best information from our documentation, which is at this URL, this uaf-rcs.getbook.io, etc. But basically, debug is for jobs that you want to, like if you're just testing out your code to make sure that it runs. You might not run it to completion because you only have like an hour time limit on the debug partition, but you just want to make sure that it runs and doesn't error out immediately. Our small partition only lets you have 1 or 2 nodes. You can run it for, I think, 2 days. I think I have a table that will show the exact amount of time. And these are supposed to be for kind of like your more high throughput computing style type jobs. If you're running something that just needs single nodes, is generally what the small partition is for. Our standard partition requires you to use 3 or more nodes. These are for your more traditional HPC, high performance computing jobs. We do ask that you use all the resources that you were allocated. So if we see that you asked for 3 nodes, but you're only using 1, you'll probably get an email saying, hey, I don't think you meant to do this. Can you cancel your job and either move it to the small partition or figure out how you can use all 3 nodes at once. Our L40S and H100 partitions are our GPU partitions. They're just the different types of GPUs that are in there. The L40S is, I think, can be used for some graphical information, like graphical programming, like if you're actually interested in using GPUs for the traditional work, as well as I think for certain inferences. Our documentation has kind of a little bit more information about kind of the differences between the L40S and the H100s. The H100, oh, should also say the L40Ss only have 32-bit floating point, 16 or 32-bit floating point precision hardware. If you're doing 64-bit precision floating point operations, it emulates that, so it might be slower. The H100 has full 64-bit floating point. GPUs in the H100 are faster, a lot better for like larger models, AI models. I think you can do less of the actual like visual stuff on the H100s, just because they weren't built for that. But they're a bit more of a powerhouse, and I think they might have different amounts of GPU memory. Oh, let me actually go to our documentation so I make sure I'm talking about stuff that's correct. And I can also show the page. So our GPU information is in this GPU overview. So yeah, so our H100s have 80 gigabytes of GPU memory, whereas the L40Ss only have 48. And then I tried it. Okay, yeah. L40Ss are more for small model training, inference, and fine tuning, limited to floating point 32. They can be used for graphics and general computing as well, as long as you do not need the 64-bit precision. And the H100 GPUs are suited for large AI models, fine-tuning medium to large models, and they can do the 64-bit operations. So you can use them for large-scale simulations and deep learning that need more computational power and that 64-bit operations. We have 4 L40S nodes in as compute, and then one of the L40S nodes is our GPU login node. And then our H100 node, we only have one of those, and all the GPU nodes have 8 GPUs in them. Great. Yep. And then to submit jobs, as I mentioned before, and I'll go over this in a little bit more detail shortly, you can use srun, which is kind of an interactive way to run jobs and can be used in your job scripts as a replacement for MPI exec, but that'll be talked about in a more advanced lecture in the future. And then you can use the batch submission, the sbatch command, if you have like a script that you want to launch. Yeah, and these are our list of our partitions, the amount of nodes that you need to use. You can use 1 to 3 in debug. You get an hour total time. In our small partition, 1 to 2 nodes, 2 days, and etc. One caveat with the L40Ss and the H100, all of our just CPU nodes, the ones that do not have GPUs, are exclusive. If you get allocated resources on a CPU node, you'll have full access to that. No one else will be on that node, with the caveat that we have the analysis and BIOS partitions. Those are shared, but those are basically high memory nodes that are supposed to be used for programs that don't need a lot of CPU but need a lot more memory. Those are shared, and our GPU nodes are shared. All the other like 100 plus CPU nodes, if you're on those, you get exclusive access to it. The GPU nodes, we're asking that people limit the amount of memory that they're using for their jobs because you're sharing it with other people, and that you request the amount of GPUs that you're actually using. Because we have a limited number of GPU nodes, we really want to try to maximize the amount of people who can use them. Should also mention the GPU nodes are available to everybody now. We have the documentation now. They should be open to everyone. So if you're wanting to use them, now is the time. We just ask that you read our GPU documentation before you use them. We are going to be monitoring them to make sure that all the GPU nodes are being used by the jobs that are on there. So if we see that you've requested 8, but you're using 1, we might email you and ask you to retool your job. Yeah, I mentioned the another informational command that's pretty useful is the sinfo command. This will display information specifically about like the Slurm nodes and partitions. There's a few different ways you can get information from them, and then the kind of information that you want. This will tell you like what nodes are allocated, what ones are down, what ones are reserved or available, all sorts of things like that. And then I mentioned the saccount command, which is really useful. srun itself is used to allocate resources from the job scheduler, and then you get to actually launch your job. And then, as I mentioned before, you can use this to run parallel jobs in an allocation. We're still writing up some best practices for that because there is some overhead when you do that. And we're just trying to see if there's a way to minimize the overhead that we're seeing before really recommending that people do it that way. Your best use for srun is for like kind of interactive jobs. This command here is kind of one way to do that. So if you're like trying to debug something on the compute nodes, and you know that if you just ran it manually, you'd be able to figure stuff out a little bit faster, that's when you can do srun. And then if you do need to use like a graphical interface, a lot of this, we see a lot of this, for example, with the parallel debugger total view. You can pass it this --x11 flag, and as long as you have x11 forwarding and x11 server set up on your connecting box, you'll be able to use a GUI on the compute nodes. And then there's sbatch. So this is if you want to write up a little script and submit it to the job scheduler. So you'd want to do this because, as we've mentioned before, HPC clusters can be kind of a very busy resource. So when you do srun, you need to keep your like terminal open. You'll have to wait. You might not know when you finally get allocated those resources. So like it might happen at 2 in the morning, and you don't want to have to like, set an alarm to check or set up some way where it's going to email you and then set off an alarm so it wakes you up so you can, run on the compute nodes. You'll want to just be able to write some commands that you want to run, send it to the job scheduler, and then just let it run when it runs. So you can create a shell script, typically Bash, that's our default shell, to run your program. Um, the same sort of flags that you pass to the srun command are usable in sbatch. You just have to put this number sign, hashtag, pound symbol, whatever you want to call it, sbatch in front of it. And then when Slurm reads your batch script, it will know that these are the flags to pass it. And our recommendation, whether you're using srun or sbatch, is put in a time limit. Um, and the job scheduler has a scheduler in it. And if it can see that your job's only going to take, 2 hours, and then it sees that there's like going to be an open amount of nodes just for a couple hours, it can slot your job in there, even if other jobs might have higher priority, but they might need more resources than that. So it just helps the job scheduler really prioritize the amount of resources that are available. Yeah, one of the great things about using SBatch is you can submit your job without having to wait for a node to be open. And then, again, this will probably be covered more in the advanced HPC lecture, but you can implement job chains to have like a full workflow for your job without having to like manually submit jobs as they finish. So you can like write a batch script that then you can like submit, like 5 different jobs, but like jobs 2 through 5 might only launch after the previous job has finished. So you can say like, and so in like job 2, you're like, only actually ask for resources once this other job's complete. And then that way you can submit this as like a single workflow. Um, and then you can just, walk away. You don't have to, see that job one's completed, then launch the next. So you can do all sorts of powerful things with batch scheduling. Yeah, as mentioned before, these directives can be used either with srun or sbatch. And srun again launches a job from the command line interactively, sbatch as a batch script. And yeah, with srun, you pass arguments like most command line programs. You can either do dash dash or dash a letter. And then the sbatch directives look with are just preceded by like number sign sbatch, then the flag. These are some just common srun, sbatch directives. Time, the format for it is day, t, then hour, minute, seconds. And then a lot of these have like the long flag, dash dash time, or short flag dash t there. End tasks is the number of tasks that Slurm will allocate. This is more important if you're doing MPI sorts of programs because you can then your MPI program will know how many tasks it's allowed based on this number. So, technically, if you're doing like a multi-core, you might not need to do this since you get exclusive access to a node, but it's still very good practice to do this. Partition, dash dash partition, or dash P, that tells you what partition you're going to be requesting resources from. Tasks per node is how many tasks you want on a single node. Um, we recommend doing this rather than saying like I want 3 nodes and then give me 10 tasks per node, just because we just find it easier to ask for the total number of tasks that you want. And then to get the number of nodes that you want, you say how many tasks per node you want, and then your end task divided by tasks per node will tell you the amount of nodes that you get. We just find that being very specific just clears it up for us and also just makes it clear to you when you write your programs. There's this output flag. So this will display the data that like your script prints out, your batch script, or basically what's getting written to the terminal. This won't be the output for your program. So if you like have a Python script that does a bunch of calculations and you're saving it in like, results.txt or something, um, that's not what this output refers to. That your results that your Python program will be writing to the file, that'll still be written to that file. This is for like, if you have like your batch script, say, like starting step one or something, or if you have timing information, that's the information that'll be displayed in this output file. There's also a corresponding error flag. So if you've used Linux, there's like standard output and there's standard error. The error flag just will write what's getting written to standard error if it's not also getting written to standard output. And this %J, I think I talked about this in a little bit, but there are some basically character substitutions where your Slurm will see like %J and then replace it with like the job ID. And there's a whole bunch of these. They can just be useful for filling out information. There's this mail user and mail type flag. Basically, mail user send an email to this user, this email address. And then you can say, oh, email me when the program begins, when it ends, when it fails, when it reaches its time limit. You can also say, I think there's time limit _50, _80, and _90. You're like, okay, it's job's 90% done. Email me so I can like ask for an extension or make sure that it's actually going to finish in time. And finally, there's this constraint flag. A lot of centers use this for like specifying between like GPU or CPU nodes or even particular generations of nodes is what we do. Basically, we've labeled most of our nodes with like what processor type they are, specifically our Intel flavors because they are 3 different generations. And so you can request like, hey, I want Sapphire nodes, the Sapphire Rapids ones. And when Slurm goes to allocate you resources, it will only look at the available Sapphire Rapids nodes. Whereas if you do like, hey, give me just the Haswell nodes, it'll only ask for the Haswell ones. So that can be pretty useful if you are needing like specific resources. And other centers sometimes use it for like, oh, interactive or you know, shared nodes or something like that. Oh, and these are the SBatch replacement symbols. These are the ones that are kind of useful that I found. %J and like in your SBatch script will replace the %J with the job ID of the running job. %U will be the username. %X is the job name. You can pass job names to Slurm. It just really affects what's listed when you do SQ and nothing else, but maybe you want that in your job script and then %N what node name stuff is run on. And this is just a pretty basic job script example. So you can see this is a batch script. So, I have my bin bash. I forget what that's called, but the thing that says, yeah, this is a bash script. Um, Number signs, pound symbols, hashtags, those are comments, except if it's immediately followed by this SBatch. If it's followed by SBatch, that just means that Slurm is going to read this as an argument for srun, basically. You say like the job name. So when I do run SQ, it'll pop up as example job, partition and tasks, time limit, mail user, and output. And then once you set up all your SBatch directives, you can basically put in what you would normally type to run your job if you're running it interactively. You can just put that in the script and then it'll run it on the compute nodes. We always recommend purging the modules, just make sure it's clear, then loading the modules that you absolutely need, and always load Slurm, just because some of the your JavaScript stuff might need access to Slurm commands. And then, yeah, but basically all I'm doing here is I set a date, run a simple little script, set an end date, do some do some subtraction to get the number of seconds that it took. Um, And I'll show you this quickly as well, but we have open on demand as another way to access if you don't want to do it through SSH. Right now, this is currently in beta form, so we're still doing works to it. You might see things tweak. You might see stuff, um, get taken offline as we like update or install software. So we would recommend this being your only method of logging in. And currently at the moment, since we are in this beta format, if you want access to on-demand, you'll just need to request it. We'll add you to it. And then I have a few demos to run and then go from there.
Okay, before we go to the demo, a couple of questions that I commonly get from other scientists. So, how much storage is allocated by default per user when they get an account? Is it 50 gigabytes?
Oh, it's 50 gigabytes in your home directory. Your project, at the moment, you get 1 terabyte shared with your whole project in Center One. As we're bringing this BGFS file system online, projects are going to get 3 terabytes, and that's shared through all members of your group. And then each PI gets 30 terabytes of archive storage they can split between any number of projects. So one thing that we've been seeing is Google Drive, the university's Google Drive allocation is getting shrunk. If you do have like data sets or stuff in Google Drive that you might need to move elsewhere, come talk to RCS. Archive might be a good spot to put those. But yeah, so you get 30 terabytes of archive tape storage to share within. Um, Additionally, as part of the condo model, you can purchase additional storage. There's also online storage you can purchase as well. But the subsidized tier is 50 gigs in home, 1 terabyte per project in Center One, 30 terabytes in archive per PI.
And is there a way to get more storage, so yeah, you told the limits, and
Yeah.
what is the cost of?
Sorry. I can take a look real quick. This must be the quickest way of doing it. So our service rates are so for Center One, it's about $150 per terabyte per year per project. For online storage, it's going to be a little bit cheaper. It's 120 terabytes per $120 per terabyte per year. If you have less than a terabyte, and then if you have more than a terabyte, it's $90 per terabyte. So this is what we call our lease storage. So this is like we have some storage that you can get. If you want to actually purchase disks, so say you want to buy like a server with a bunch of disks in it, basically you buy the hardware, you pay us for 20 hours of labor, and then I think it's under warranty, it's a certain cost per terabyte per year. And then archive is $50 per terabyte per year, basically.
So it feels like you have a website for that. Is it in the same documentation area or?
I think I have it listed. I'll make up a slide that puts it in there just for contact. I think I have it in the section about how to get accounts, which just for that real quick, new users, basically, we have a project account form if you're a PI. If you're staff or student, there's user account application. So I'll just show these off real quick too. You need to put in your name, email address, UA username if you have one, what group you're affiliated with. Project title, we use this just to kind of come up with a Unix group name, project description, what you're asking for, and then any additional information. So that's what PIs need to fill out. And then staff and student basically just need to fill out their name, email, username. If a project's already spun up, there should be a project ID that we give the PI, and they just need to put that there, and we know between that and who the principal investigator is, that's kind of our verification. If you're like spinning up a project at the same time that you're asking users to sign up, just put pending in here and we'll know to match it up. And then If you have a different shell that you want to use, uh, you fill that out. Yeah, and if you do have collaborators at other universities, they just have to send us an email with guest account application in the subject, and we'll get them a sponsored account. But yeah, and then I showed off, I think, our general documentation, but just Gitbook site, we have a whole lot of information starting from like logging in and whatnot to using GPU nodes and things like that. Um, this is always constantly a work in progress, so we're updating it as best we can. Any other common questions that you get?
No.
Okay. Yeah, cool. Then I will do some very quick examples. All right, so this is open on demand. Once we get you access to it, you put in your UA username, your UA password. You can log in. Then you'll get assigned. You might get a thing that you need to click through. That's basically just a beta message, but we're going to put in an actual like agreement once we move this out of beta. That will have everyone have to click. Just basically the yes, I know I'm logging into systems. I'll use it, only for good, etc. So there is a file manager that you can do access. Right now, it only goes to your home directory. We're trying to come up with the best way to do like our online spinning disk, our parallel file system and archive, like the best way to allow you to access that from here. Those are some of our next steps, but you can edit stuff here. You can look at scripts or whatever if you need to as text files, um, and go from there. Um, you can see what active jobs you currently have in the jobs tab. There's like a job composer where you can create jobs from here. We have like a basic script, for example, that you can create from like a template. Um, that'll be down here, and then you can submit jobs. So if I want to like a new job from the default template, you'll see this is default services sequential job. If I click it, I can like edit my job submission script and things. Um, I think there might be some job options, like if I wanted to, sample job, yeah, job. Um, I'll change the name, and then I can change, the script here as well if I really wanted to. Um, and then to launch it, you just click on the job, hit submit, and then you'll see that it says queued, and then once it runs, it'll run. And it's ready, and you'll see that it's completed, and I have output files, um, and my default my default output file. So go back, open on demand. You can see kind of the cluster status, what nodes are available, how many processors in use, how many GPUs. Here as well. Oh, one thing you do in the active jobs, you can see all the jobs that are currently running right now as well. If you want to log in without having to use SSH, you can log in through here. Again, UA username and password, and you'll see that you're on Chinook right now. Exit, close there. And then finally, there's some interactive apps. We don't have desktop set up quite yet. One of the things you can do with Open On Demand is get desktop access to your compute nodes. The one we do have set up is our Jupyter notebooks. So if you do want to run a Jupyter notebook on Chinook, you can do it this way. One thing that we have run into that I think we need to document a little bit more is you do have to build your kernels, your Jupyter core kernels in a certain way, if you want to use extra things. The default kernel should work, but if you need like GPU programs in there, you might need to build it yourself, and we're working on documentation for that. So yep, after we waited, we can see that it's running. I can connect to Jupyter, and I have a Jupyter notebook, and I can do a new kernel, which I think this is the default kernel, so this should work. And you can see I can get a Jupyter notebook there. But yeah, building your own kernels will, the main reason that this can be a little difficult is this uses a specific module that you have to load and then install when you build your module. All right, and then I think the last example that I'll show is just a couple of jobs. Let me stop sharing real quick just to set up my screen properly. Okay. Let me share again. Desktop one. Okay. So right now I have two terminals. Let me increase the size of that one. I'm logged into Chinook. I'm going to center one directory. And we'll just, since we're running a little low on time. So first off, I want to do like an sinfo. This will give me a, in this terminal will give me kind of the state of the partition, what nodes are idle, what nodes are like reserved, what nodes are allocated. But you're going to have a node that's currently down. I can use SQ to look at what jobs are currently running, which is the R, and which ones are waiting. The PD means pending. And then the tool that we wrote is QMap, which gives basically the same information, but organized a little bit nicer. So you can see the jobs that are currently queued, the jobs that are currently running, and then there's like this graphical interface of what nodes actually have jobs running on them. We don't have the GPU nodes in here yet, but it's something that we're going to add.
Even if it takes some time for the demo, it's completely fine if you could send me some video recorded file afterward and I can merge them in.
Okay, yeah, we can do that. I mean, I don't. Yeah, I'll do that.
If you can do it in another 10 minutes.
Yeah, I think I can do it in another 10, but if there's extra stuff, we'll do it that way. So if you want to look at like the list of constraints and stuff, you can do this sinfo-n-r-l, which kind of gives individual information about each node, but you can see like what nodes are Skylake nodes, what nodes are Sapphire nodes, what their state is, etc. I think we said SQ, and then I just want to show off the S account command too. So if I do like S account dash capital S, three, like that, it should list all the jobs that I own that have started since March 15th. Hopefully this runs. Yep. So these are all the jobs that I've run since the last day or so. So this can be useful if I'm like looking for specific information, like, okay, what jobs have I run? And then I can pass it like a -O flag and say like start, end, and that should show when each of these jobs started and when they ended. If you mat, there's a -O format, and if you man page it, it tells you all the different fields you can do. And finally, I just wanted to show a quick example of why parallelization matters. Oh man, this is hideous as a, let me see if I can do dark mode here. Oh, dang it. All right, let me log in again here in dark mode, and that might hopefully look a little bit better. Okay. All right, so this is my Slurm script. I have my SBatch directive. I'm gonna have it email me. This is what my output is. And basically all I'm doing is I'm using a rot X Caesar cipher to rotate letters on some text that I have. And so I'm going to run it in serial mode, in parallel mode, which I'm using with the using what's called background processes. We'll talk about this in a future lecture. And then I'm doing it again with even more nodes. And then if I just do an S batch, reservation, created a reservation for this, just so I made sure I had nodes available. Okay. All right. I'm just going to not even use a reservation. I think we have nodes available. Just real quick. Just see if joining that table. Oh, my partition. Okay. Hopefully. All right. So this screen here is, see if it's actually running properly. See if I'm on the right nodes real quick. 70 and 71. Yep. So what should be happening any second now is, oh wait, let's do it this way. There we go. I'm running this Python script in serial format. It's going to take about 40 seconds or so. And you can see that's just running on a single node, even though I'm using two nodes. And you can see, yeah, now I'm running 8 nodes all at once. I mean, 8 processes all at once, and now 24. And you can see that I was doing basically the same amount of work on each one. So if I look at my output file, which now exists here, and you can see that it's subbed in the job name. When I look at that, when I ran it in serial, it took like 42 seconds. When I ran 8 jobs in parallel, it took 5 seconds. And I did 24 because I had 24 processors. It also took 5 seconds. And then I guess my last thing that I should probably show is if you want to run something interactively, you do like srun-p debug -n24. I want 24 tasks, 24 tasks per node, and then give me a bash shell. You'll see that it changed. I'm on KP Galloway at N0. If I do a host name, I'm on n0.cluster, and now I can work with this interactively. Yeah, so that should be about it for the demo. If you ever have any questions or anything that RCS can help with, feel free to send us an email at uaf-rcs@alaska.edu, or you can call our help desk, which is their number is on the website. I think it's 450-8602. But yeah, always happy to help. Thank you.
So one quick question. So for an interactive job, is there any time limit?
It'll be the same time limit as the partition you ask for. So yeah, and one thing we've debated, and please let us know if this seems like a good idea. We can also maybe create a specific interactive partition as well.
And for the open on demand interactive works through Jupyter Notebook, is there any time limit?
It'll be the same with what partition. Yeah.
Everything.
Yeah, it's based on the partitions. Yeah.
Awesome.
Right.
All right. Let me just close it. So well, thank you, Kevin, for the wonderful lecture. So all the materials and everything will be available on our Data AI Lab website. And well, I will share the link with all of you very soon, and have a wonderful day. Thank you.
All right.